Hello and welcome to stable and unstable nuclei. Okay, so if we have two protons near each other, they are going to repel. And they're going to repel more and more strongly the closer and closer you bring them together. So how, if we have this situation, how on earth do we ever end up with a nucleus where we've got protons in very, very close proximity to each other? How is that ever going to be stable? Well, it's stable because we have something called the strong nuclear force. And the strong nuclear force acts between all nucleons. So this strong nuclear force is very, very weak at large distances and gets stronger the closer the nucleons get to each other. On this graph, we can see that the electrostatic force, that repulsive force pushing the protons away from each other, increases as you get closer and closer. So on the x-axis, you have separation, the distance they are apart. Here are the very, very small distances. Here are the very large distances. And the strength of that repulsive force is increasing as you get closer together. So we should be familiar with that concept already. If things are repelling, you bring them closer together and they repel more strongly. The strong nuclear force changes very differently to this. So the strong nuclear force gets more and more attractive the closer you get. So as that separation decreases, as you get closer and closer, that attraction gets more strong, it gets higher. The force of attraction increases as you get closer together. So if we look back at our example over here, that strong nuclear force is very, very weak while they are far apart and gets much, much stronger when they are closer together. So these forces would be, say, that and that, much stronger. So as the nucleons are pulled together as they approach, that helps keep the nucleus together. And it's not just protons that this happens with, it's also neutrons. So for example, if we have a proton and we have a neutron, they are going to feel the strong nuclear force as well. So as the nucleus gets larger and larger, it's helpful to have more and more neutrons. And what you'll notice is that the heavier nuclei tend to have a greater ratio of neutrons to protons. So at very, very small sizes, nuclei tend to be stable when there are an equal number of protons and neutrons. When you get to the very large nuclei, they are stable when you have roughly 3 neutrons for every 2 protons. So let's sketch that. In a very, very small, stable nucleus, you tend to have situations where the number of protons are equal to the number of neutrons. When you have very, very large, I'm talking 20, 30 protons, that number increases. So for every one of these, you're going to have, for every 1 proton, you're going to have 1.5 neutrons. So that would be a stable arrangement for a very, very large nucleus. The strong nuclear force does something quite strange if you get too close. So we have this increase in force, the closer you get, up until a certain point, and then it suddenly decreases. That force of attraction goes to 0 and then turns into a repulsive force if the nucleons get too close. And this is to stop them from smooshing into each other and becoming one object. It's to keep them as separate, discrete objects and stop them from smooshing into each other. Let's have a look at different types of nuclei and their stability. Okay, so I'm just going to take a moment to have a look at this graph because it is quite complicated. So here we have a graph showing the number of neutrons against the number of protons. So we can derive the mass number from this, for example, by adding those numbers together. We've got a line going up the centre here that represents 1 to 1. So 1 neutron against 1 proton. That's the 1 to 1 line. And you can see that down near the bottom here, we have the situation that I described earlier. The dark dots, the black line that is travelling up through here, every single one of those pixels represents a stable nucleus, a nucleus that is going to stick around and stay with us because it is perfectly balanced. And down near the bottom with the very, very low mass numbers, it is following that 1 to 1 line. So very, very small masses, you get a stable nuclei if the number of protons is equal to the number of neutrons. As you get higher up, that line of stability starts to stray away from that 1 to 1 line. It's moving away from it. And higher up, it's following that 1 to 1.5 line. So for every one proton, it's stable if you have 1.5 neutrons. And that's this line up here, that's that gradient. And we can use this understanding to predict what kind of decay we're going to get. So, for example, if we have a nucleus that is following this gradient, these black dots here, then it's not going to decay. It's perfectly stable and it's fine. Everything is balanced. There's nothing it can do to make itself more stable. You'll notice that those lines stop at about this point here. That's the last stable isotope. If you get any bigger than that, you are going to decay into something more stable. And that's usually by alpha decay. And we've got an example of that up here. So we've got radon, which is larger than that 82, so it's going to be unstable. And it's got a mass number of 219. 86 of those are protons, the rest are neutrons. And it's going to decay into polonium. And it's going to do so by alpha decay. Alpha is two protons, 2 neutrons, and it looks like a helium nucleus. So this polonium is going to decay, this radon is going to decay into polonium, and it's going to do so by alpha decay. So it's going to emit an alpha particle. Sometimes that's written as the helium nucleus, but most of the time it's written as the alpha particle. There we go. So what's going to happen is that the radon is going to eject 2 protons and 2 neutrons, 4 objects in total. So we need to balance this equation. It had 86 protons, and that's going to go down because 2 of those were ejected. So that 86 goes down to 84, and that's what tells us that it's going to be polonium. It's also going to lose 2 neutrons, taking the total loss down to 4. So to that 219, that mass of 219 is going to be reduced by 4. 219 take away 4 is 215. So that's going to be our alpha decay equation. Okay, let's look at another example. So we've got carbon 14 here. We know that it's carbon because it's got 6 protons, and the isotope that we're looking at is carbon 14. So that means that 14 take away 6, there's going to be 8 neutrons here. And if we do a quick calculation, we can see that this is not lying in the 1-to-1 ratio. If this was a stable isotope, because it's such a small mass number, we would assume that if there's going to be 6 protons, then there's also going to be 6 neutrons. But there aren't, there's 8. So there are too many neutrons to make this isotope stable. So what happens is that it gets rid of one of its neutrons. So we want the neutron number to go down. So what happens is that that neutron changes into a proton and an electron. Let's have a look at that over here. So a neutron can change into a proton and an electron. We have something with no charge turning into something with a positive charge and a negative charge. So those two cancel each other out and the charge is being conserved. We go from no charge, a particle with no charge, and it splits in two. Something with a positive charge, something with a negative charge. And the negatively charged object, that electron, is ejected from the nucleus. So what we see is that the proton number is going to go up because one of those neutrons has turned into a proton. And we get the electron ejected from the nucleus in the form of a beta minus particle. And a beta minus particle, that's just an electron. Okay, so let's summarize what's going on. We are going to have our proton number go up. The mass number stays the same inside the nucleus because we're not gaining any nucleons or losing any nucleons. One of this is turning into a proton, so the proton number goes up, but the nucleon number stays the same. And the electron that was created is ejected from the nucleus. Now, when scientists were studying this is beta decay. When scientists were studying this, they noticed that the kinetic energy before and after the decay did not balance. There was energy missing. So what they did is they looked more carefully, they did some mathematics, and they discovered that there's actually another particle being given out at the same time. And that's a neutrino. A neutrino is a very, very small object. It's very, very difficult to detect, and it's quite a complicated concept. You need to know that an antineutrino is given out during beta minus decay, and a neutrino is given out during beta plus decay. We're going to talk about beta plus decay next. But the reason why this is in the equation at all is to balance the energy. Without it, the equation is not balanced. Okay, let's have a look at nickel. Nickel with a proton number of 28 and a mass number of 56. So this is nickel 56. So there's our 28 protons. 56 minus 28 is 28, so it's got 28 neutrons. Okay, so 28 protons, 28 neutrons, there's that down there. And it crosses here, and we're in this orange area. So what we can see is that it's not following that black line here. We're in this region below the black line. So we would expect at this level to see, for 28 protons, we would expect a stable isotope to have more neutrons. So it's got too few neutrons. This number is too small for the number of protons that it has. So that strong nuclear force isn't quite strong enough to hold together the nucleus. We need more neutrons in order to stabilize this nucleus. So what's going to happen is that one of the protons is going to turn into a neutron. So we're reducing the electrostatic repulsive force and we're increasing the amount of strong nuclear force compared with the electrostatic. So we're making it more stable by reducing the electrostatic repulsion. So that proton's going to turn into a neutron, but where did all of that positive charge go? This particle has a positive charge, and we're turning into something with 0 charge. So we're going to need another particle as well to take away that positive charge, and that's going to be in the form of a beta plus particle. And to balance the energies, we're going to end up with a neutrino as well. Okay, so let's do that for this nickel 28 equation. All right, so we've got too many protons for the number of neutrons. So one of those protons is going to turn into a neutron. We're not changing the mass inside the nucleus, so that is going to stay at 56, but we are losing a proton. So this goes down to 27, and that means that we are changing the element and it turns into cobalt. That proton needs to take away its positive charge in the form of a beta plus particle, which is an anti-electron. And we have a neutrino. So this is a neutrino. And in beta minus decay, we have an anti-neutrino. So these are antiparticles of each other. They have the opposite properties where that is possible. And here we have a positron. And here we have an electron. And because these particles are being given out during beta decay, they're called beta particles. So that's why the naming system is that way.